So let's start adding loads to the model. Now in my example, I've got a dead load and a live load. So depending on which class we're in, we either will factor these loads if we're in the steel class, or if we're doing the 230 or 485 class, we're not really into factored loads yet. So I'll kind of do it both ways. One where I just have a single point load, and then one where I'll actually put in the dead and the live load. And it can be helpful to do both because remember, when you do deflections, you want to use unfactored loads. Okay, so let's start with loads. And again, I find this a little bit strange how you enter this, but let's say point loads. Okay, so node 1, that's where my loads are being applied. So I have a Y direction load, so 125 is my first load, and that's a dead load. And load group, this is something that it gives you. Now I'm going to call that D. I'm going to call that my dead load. So I apply. Now I've got 125 kip load here. Node 1 again, and I'll call this my live load. And that factor, or sorry, that not factor, that magnitude of load is 175. So let's apply that. Okay, so let's also do just combine dead plus live. So if I added those two together, what would I get? 300 kips. So negative 300. And I'll call that unfactored dead plus live. Okay, apply that. And if I want to do a combined factored load, we can do that as well. So I'll say 1 and negative 430. So if I apply 1.2 dead times the 125 plus 1.6 live factor times 175, so 1.2 times 125 plus 1.6 times 175, that'll give me 430 kips. So that's the total factored load. So I'll say this is the factored dead plus live. And let's apply that. So you can see all these loads stacked up. Okay. So now we have load combinations. Okay, so this is where you can get really fancy. If you go to design codes, you could bring in all of the ASC 7 codes, LRFD codes, ASD codes, and you have all these different combinations, and if you enter your loads correctly, it'll put them in all the right factors and do all these combinations for you. Okay, so we're only doing one combination, dead plus live, so again, a little bit more advanced for us. Let's just stick with one combination. All right, so dead factor, D factor is 1, 1, 1. Let's see now. I tell you what, let's go. I'm going to enter it like this in my spreadsheet. Okay, so what we typically do in the steel class, we factor the dead at 1.2, live is 1.6. I have zero factor here, zero factor there. So I'll call it factored. Okay, apply that. So this should give me the same results here. If I put in 0 here, I put in 1 here, 0 here, and 0 here. So what I've done is I've combined the loads together in this particular load group, and then I'm just using a one factor here. So if I run combination 1 or combination 2, should get the same result. Now this one, this is unfactored. So that's what I'm doing here. So that's 1. Everything else should be 0. So let's apply that. All right. So I should have all my loads in here. I've got my load combinations. Let's see. Next thing I have to do is solve it. Well, let's save it first. Save this into trusses. So I've already got my model here, but let's just say in class example. So 100 North Riv class example. Okay, so now it's saved. All right, so now I'm going to solve it. And I'm going to keep it real simple here. I'm not going to do a buckling analysis. It can actually do some pretty interesting stuff. It can actually check buckling of all these different shapes, but we're just going to do the basic analysis to get all our forces, and it will do analysis of all the shapes. It just doesn't do that more sophisticated buckling analysis. And there's some other dynamic frequency. If you had seismic loads on buildings, or you want to check the frequency or period of the building, you can do all that types of analysis as well. I'm getting into more seismic, but we're going to stick with a simple one here, the linear static. So let's solve that. Okay, so I believe it will solve all of our different combinations. Yeah, so all these combinations come up. So if I look at this one or this one, it should give me the same results. So this is the unfactored dead plus live. So this one I'll check if I want to do deflection. So let's just bring that up, displacement. Okay, so that's the displacement due to unfactored loads. Kind of what we'd expect, right? We've got a pretty large load pulling down on this. The end of this is going to deflect down about 1.3 inches. Okay, so let's go back and we'll do the factored dead plus live. So obviously it increases the deflection because we're using larger loads, right? But those aren't the actual loads being applied. Those are the increased loads, right? We use to check all the steel. To check the deflections, you want to use unfactored. Okay, so a couple nice things we can do here. We can do truss hand calculations, right? Method of joints, method of sections. If you want to cut a section, it'll do that for you. Go through method of joints. Kind of gives you the statements. What we're assuming here, everything pinned, goes through to the reactions, goes through each joint. So it's really nice, going through and giving you all the various steps. So this part of the program I like. It's great for a class like ours where we're trying to do these by hand, and then we can take it into a program like this and check our work. Okay, so let's take off the displacement. Click on a couple of other things. So moment, all right, click on that. Well, it looks like I've got 0 moment, which is correct for a truss. So if we model this correctly and we have 0 pins, if we have pins at all of these locations, we'll get 0 moments at all those locations. Now, as soon as I would start loading a truss, let's say I have a point load coming down right here in the middle of this member, you'll start getting moments. Let's say in member 5, or same thing, if I put a force here, you'll get a moment in this piece. So if we load the truss only at the panel points, we only get axial loads within the truss. Okay, so it's moments we don't want. We want axial loads. Okay. So I wish it would map these out, meaning that it would give me a thicker line here where I've got 716 versus 327, but it's pretty clear, what the various forces are. Actually, nope, that's not going to do it for me. Scale, let's see if this will. Nope, it doesn't do it. I was hoping it would actually map these out and make them bigger, but it does not. Okay. But we can go through these. We can click on these, take off that, go back to moment, go to axial. Okay, so I've got tension in all these, and this is our convention, right? We draw the arrows away, or now that's interesting. The opposite convention that we typically use in our hand calculations. Typically, when we draw this thing in, this would be a tension member here. We would draw the arrow pulling away from the joint. We would draw it pulling away from the joint. So they actually flip it here, which is kind of odd. I don't know why they do that. Maybe they're saying that this is pulling on the member, this is pulling on the member, and this is pushing on the member, this is pushing on the member. But we typically, when we draw our joints, we draw an arrow away, we're saying that that's in tension, that the member is pulling on the joint. So I guess if these are the forces within the member versus the forces on the joint. That's the way that I'm doing it. When I cut them at the joints or cut them at the sections, I'm drawing it forces in and out of the points itself. So blue is in tension, red is in compression. Let's see, we can go through, we can do a single member, and we can get a report on that if we wanted to. The next thing is design. So if I go into my ASCE code, LRFD, so these are the places where you put in your phi factors, and these are all built in for you. These are the members. Now this is where you'd put in the unbraced length. So if you're doing a beam and you're talking about lateral torsional buckling, let's say that you had braces every 4 feet along these compression members or along these beams, this is where you would change it. You don't do it in the modeling, which I find it kind of odd. So you have to go into the design module, and this is where you would change these lateral torsional lengths. So this is what we typically call L sub B when we're doing beams. Now in terms of buckling for the columns, you have the strong and the weak axis, so you could change these values here if you had bracing along those members. Now in this case of this truss, there's no way we can brace these, right? These are completely unbraced from one node to the next. So we hit check once we've got everything in there, and it checks all of our pieces. And so it looks like we're pretty good, except for this one here. So this is a pretty long piece. This is 32 feet long. Has a very large force in it. I think it had like 500 kip feet, or sorry, 500 kips in it. And so we're just over. We're 1.1 in terms of the utilization. So you want to be 1.0 or less. And so this one fails, but everything else passes. If I go back to solve, I just want to go back and look at the axial force that we have. Yeah, so this is 573. It makes sense here. This force and this force would be the same because there's nothing else coming into this joint that would give us an X component, right? So you're going to have a translation of force right across here. The reason that this one fails and this one doesn't, this is only 24 feet long, where this is 32 feet long here. Okay, so a couple other things we can do. I'm going to save this again. So if I look at a picture of the actual truss, so this is up at the top of 100 North Riverside. Chicago River is just to my right here. This is the new Getch building, 150 North Riverside, that uses the same truss to transfer the loads into the core and also away from the train lines going under the site, similar to this building. But this building, it's actually hanging this column because it can't go down because there's a train line here below it. So this truss obviously has support here, and support here. For simplification, we had to remove one of these supports so we could solve it using our methods of statics. Let's see, and then we have this additional member, diagonal member here. So let's go ahead and add those in. I'm going to go back to the model, go back to members. I want to go to, oops, truss, and I want to go from 2 to 6. So I'll apply there, and then I'm going to add an additional support. I'll put in a roller at 3. If you do add additional supports along a truss, it's probably a good idea to put these as rollers, because if you start putting them as pins, the truss is not going to behave very well in terms of, allowing it to expand and kind of contract and actually utilize the members. What you'll get is arching action. Let's say you got a pin here and you got a pin here. This thing is just going to arch between those two and push on this and push on this. It's not even going to engage the bottom chord. So if you have, obviously at least 2 supports, one's a pin, one's a roller. Even if you add a third or fourth, go ahead and put that as a roller as well. So I've got a roller there. Okay. Make sure I apply it. And now I can solve it again. So we can solve it with this program, but if we try to go back and do it with statics, we would not be able to do it. I'd be curious how the hand calcs actually work. No, it stops because it can't. It can only do one joint. So we get some differences here. We do get quite a bit of compression. Let's say in this diagonal piece here, this force gets to be a lot smaller. Again, we wouldn't be able to solve this with this crossing in here. This truss becomes too complex for us to be able to solve. But it's similar in terms of the points and the reactions here. If I pull up the reactions, you still get a large an upward force here, so you have to have a pulling it downward here, but it actually does share it between this piece and this piece. So that's the great thing about having this additional support in here, that'll spread out this tension load between this piece and between that piece. Okay, so that concludes that model.